Hello guys, good morning. I am Aryan Agrawal and I will be taking a session today. As you all know, as you can see that the session is on machine learning in astronomy. Before we proceed, can I just get confirmation that I am audible? My voice is clear. Okay, fine, cool. Uh, for any queries during the session, you can just like raise your hands and we will allow you to speak. Then. My screen is visible, right? The presentation. Okay. So first we will have a look at this presentation on machine learning. We'll first cover the basics of machine learning, then the specific machine learning for astronomy, and then we will have a demo for like creating a simple model for the topics that I have told you already. The asteroid has predicting asteroid hazardness and the also predicting exoplanets. So let's start with the presentation. So right, machine learning and astronomy. Like the machine learning is the buzzword currently. Everyone is trying to learn machine learning, data science, artificial intelligence, and everything. So let's see what's the hype about machine learning and what is it exactly. So the topics that we'll cover today is the basics of machine learning, the different kinds of machine learning. Why do we need machine learning in astronomy? Then what are the applications of machine learning in astronomy? And finally, we will have some hands-on demonstration for simple models, right? So what is machine learning? As you can see the definition here, which was given way back in 1959, it is the field of study that gives the computers the ability to learn without being explicitly programmed. What does this mean? It means that we are giving the computer the power to learn by itself. How is it different to software development or anything? In software development or the old fields of computer science, we give the machine a specific sets of instruction and it is allowed to just complete that specific tasks. But in machine learning, it the information that we give the machine, it takes up that information, learns from that information, and can take up decisions on its own, right? So that is the difference between machine learning and basic software development. We are giving the machine the right to learn new things and take up decisions itself. So why can anyone tell me why the fields like machine learning, AI, and data science have been like sort of boomed recently, and they have not been in they have not been very available since very long. Why is it that it has taken up very recently? If you go back 5 to 6 years back, there was not many applications of machine learning, or not many people were aware about machine learning and AI. So what do you think has changed now? Not due to OpenAI. OpenAI was like those things also came now, no? Yeah, as Swastika said, because we have larger data to analyze now. The most important thing in machine learning or data science or AI is the data. The data is the most important thing in the world right now. The software giants like Google, Microsoft, Facebook are so valuable because they have data of lots of users, millions and billions of they have data for millions and billions of users, and this data is what gives them the earlier we didn't have this much of digital data to analyze, and that's why these fields are not very prevalent. But currently we have a large amount of digital data which can be analyzed and worked upon. So that's the reason that the machine learning, yeah, there's an increase in demand in automation and all, but people didn't know something that something like automation existed a few years back. They didn't know that we can do these things. So these things have been possible because of the availability of data. The ability of large amounts of data has allowed us to implement all these things, machine learning, artificial intelligence, and data science and all. So data is the most important thing, right? So we'll move forward. So there are various types of ML, machine learning. So the three most common or most prevalent ones are supervised learning, unsupervised learning, and reinforcement learning. Can anyone just look at the name and tell me what does supervised learning mean? If anyone wants to speak up, they can also raise their hands.
Yeah, so supervised learning, in that we'll give the computer an input and its desired output. Like we give the input and output and make the machine learn that for what type of input, what type of output should we give. And so if we give
Correct.
like a lot of output according to the input, then it will learn and then try to make outputs on its own.
Yes, yes, very good. Yeah, so as she said, in supervised learning, we give the machine a set of data which has which has the input and the corresponding output. So it knows for what kind of input, what kind of output comes. And after that, after training the model, if we give the machine a new set of input, it will automatically give us a new set of output, learning from what input and output we have given it earlier. So as you can see the uh, definition here, where the model is trained on labeled data. The output is called the label, and the what input we give is called the feature. So based on the feature, we are giving it the different labels to different data, and later when we give a new input, it will predict the output. So it might be correct, it might be wrong, but as the more data we give, the more inputs and outputs we give to train the model, the better predictions it will make when we give it an unlabeled data later. So this is supervised learning. We need to give it a specific set of input and output for it to learn. So what's the first? So the first kind of supervised, there are like two classifications in supervised learning. The first one is regression. Uh, what is regression? Regression is basically creating a relationship between given independent features x and dependent features y. As we have studied in linear algebra, that y equals to some mx plus c, where m is the slope and c is the intercept. Similarly, in regression, we sort of create a line or polynomial or anything. The regression that I will demonstrate today is the linear regression, which just creates a straight line to fit the data. So analyze what is the definition of regression? Analyze the relationship between a dependent variable and one or more independent variables. So the independent variables x can be more than one. Like let's assume an example of predicting house prices using different features. So what can be different features? The size of the house, the number of bedrooms it has, the location it has been built. So there can be n number of features, and we give the machine the different outputs for those features, and later we predict the output using those features. Do you have any questions till now? Okay then. So you can see the graph here. These are the points, different points that have been plotted corresponding to different x and y values. We are just looking at single variable uh, uh, system, which means there's just one feature now. So with different x, there are different values of y. So as you can see, we have tried to fit a line. What things that we learned, like the basic linear algebra, where y equals to mx plus c, all the points lie on the line. But here, all the points can't lie on the line. There are so many points, and we can't fit them on a single line. So we try to minimize the total error of what uh, comes out when we try to fit the line. We'll see how to calculate that error. So here's the basic structure for like linear regression, where this y cap is what we are predicting. So y cap equals to wx plus b, which is our function, prediction function. So what are w and b? W and B are parameters such as mx, m and c, what we had in linear algebra, slope and intercept. Similarly, W and B are the parameters. For a single variable thing, W becomes the slope, B becomes the intercept. But as we increase the number of features, we need to increase the number of parameters. Corresponding to every feature, there will be a W, which is called the weight, and there will be B. Sorry, I have forgot to write a B here. Plus, and there will be a plus B here, plus b, which is the bias. So bias is the fixed value that will be present no matter what are our features, which will be added upon the various parameters w1, w2 till wn. Fine. So now, as you can see here, we have tried to fit the line, but not all points lie on the line, right? So there's some error in there's some error in fitting the model. Like we haven't fitted the given input and output perfectly, because we can't, right? We can't uh, fit all the points on that single line. So we calculate the cost function. The cost function is denoted by j, which is equals to 1 upon 2m, where m is the total number of training points that we have, into summation of y cap minus y to the power whole square. So what is y cap? Y cap is the predicted value and y is the original value. So it is called least square mean error. So our objective is to minimize the cost function as much as we can. How to do it? It's based on another formula that we first um, initialize w and b to guess a value for w and b, and then iteratively add or subtract some small values till we get the best fit. How to do it? That that takes a lot of time, and it is not possible for me to explain that right now, but I will suggest you to, like, you guys, like, look up for it later. But our main objective is to minimize the cost function, get a best fit for our line so that we can accommodate at as many points on the line, and our error is the minimum. We need to get the minimum error as much less error as we can. So this is basic linear regression. If you guys have any doubt, you can raise your hands. Yes.
Hello, sir.
Yeah.
Sir, what is the meaning of y cap sign in that equation?
Yeah. Okay. So y is the original value corresponding to an x. Like here, y is 16.62 corresponding to x of 4.3. but y cap is the point that will lie on the line corresponding to that x. Y cap is the predicted value corresponding to that x, and y is the original value corresponding to that x. I hope this answers your question.
So, sir, in that equation, that cost function, that equation is done. That what is the meaning of that y cap? That in
Yeah,
that
this
is
y cap is the predicted value corresponding to an x,
okay,
and y is the
and that y.
original value. What?
Okay.
As you saw here, we can't fit the line perfectly to all the points, right? So y cap is the point, is the value that we predict that lies on the line, but y is the original value, and y cap is the value that we have predicted.
Okay,
I
sir.
hope
Thank
it's
you.
clear now. Yeah,
Yes.
yeah,
Sir,
yeah.
can you repeat about the bias, please?
Okay. Bias is nothing, just like the parameter b is called bias. So like if you see a simple linear algebra type of equation, y cap equals to wx plus b. So b is the intercept there, and w is the weight there. So w is the slope. But as you extend that model to multiple features, b is called bias. Bias means the value, like let me explain you by giving an example. Like we're predicting the prices for a house. The B is the base price of that house. That minimum this much amount is required. And let's assume X is the area of the a house. So W into X means as the area increases, the rate increases accordingly. So B is the base price that you need to pay this much, but it increases accordingly with W, with area.
Thank you.
Yeah. So I hope everything is clear till now.
Sir,
Yeah.
sir, how do we check whether if there are any exceptions or any understood data? Like in that cases, how do we do it?
I couldn't understand your question. Can you repeat?
In case of exceptions, how do we deal with the data? Like how do we analyze it? Will the
What
equation be
what kind of exception?
like, for example, the graph could due to many unforeseen criteria, there could be some exceptions, right?
Yeah. So the thing is, the model can predict what it has been taught. It can't predict, like it will learn on its own. And what you are asking, like the exception thing, there comes under unsupervised learning that we will be looking a little later. So wait for that.
Okay, sir. Thank you.
Yeah, yeah. So we'll proceed now. If you do have, if you all have any question regarding regression, also you can ask in the chat. I will try to answer those later. So let's now get to the second type of supervised learning. That's called classification. So classification is like categorizing the data, into different classes or categories. As you can see, like for an example, let's say we want to predict if email is spam or not. So the answer to that question is either yes or no. So the negative class means when the answer is no, it's zero. We assign it the category zero. This is basically binary classification where two uh we have to predict between two classes. There comes more, like we can have thousands of classes also to classify in, but currently we are looking at binary classification, where we need to classify the data into either of the two categories. So taking that example only, if the mail is spam or not. So if it is not spam, we have the values on the x-axis, like 0 at y equals to 0, because we have given the no category the value of 0, and we have given the value of y category to y category the value of 1. So we can't fit this data using a straight line now, right? We can't use the straight line to fit this data. We won't be able to do that. So what we use here is called the sigmoid function. Sigmoid function is basically gz equals to 1 upon 1 plus e to the power minus z. Now, look, what is the range of the sigmoid function? If you put in minus infinity, x z equals to minus infinity, the value becomes 0. And if you put in z equals to plus infinity, the value of gz becomes 1. So the range of this function is from 0 to 1. Just you can't have any values outside the range of 0 to 1. So this is the sigmoid function. Now, how do you fit data here? Again, you same as z equals to wx plus b. Well, now z is the prediction, like the fitting of model, or wx plus b. And the final prediction is fx, which is equals to g of wx plus v, which gives us 1 plus 1 upon 1 plus e to the power minus wx plus b. So let's assume we gave some x, okay? We gave some let's take this data, this sorry, this point. So here x equals to 6 and y equals to 1. But when we fit it according to the sigmoid function, we get the value here, which might be something around 0.9 or little less than 0.9. So we tell the model that if the value is less than 0.5, you have to predict its category 0. But if the value is greater than 0.5, you have to predict its category 1. So so this is called logistic regression. I know this is classification, but the name it has been given is logistic regression. Sorry. So we again fit the points according to what we did last time only, wx plus b, if multiple features w1 x1 plus w2 x2 plus w3 x3 up to b, and later we fit that in sigmoid function, and that gives us our prediction fx. So here fx becomes this rather than wx plus b. In regression, fx was wx plus b, but here fx is 1 upon 1 plus e to the power minus wx plus b. And we get some value from there between 0 to 1. And if that value is less than 0.5, we predict 0. And if that value is greater than 1 or greater than 0.5, we predict 1. Are there any doubts here?
Sir,
Yeah.
sir, classification is up top is a 1, sir, up is a 0, sir. Is it related or not related, sir?
What?
And if we say change any, if we change any related, sir?
Like, are you saying if we change any value that corresponding to
Yes, sir.
any x, the y changes?
Yes, sir, yes.
Are you asking that? Okay. So the thing is that mostly in classification problems, like let's say predicting cancer with the size of the tumor. So as the size of the tumor increases, the the probability of having cancer will also increase. So generally, the data in that case, the data with small values of size will corresponding to not having a tumor, and having large size will correspond to having a tumor, having cancer. So uh, yeah, mostly the data point should be first small for small values of x, and as the x increases, it should go to 1. But it is 100% possible that the point here goes to here, like the value that we have given here 1 can be 0. In that case, it will try to accommodate that, but it might fail to do so because it is a very simple logistic regression problem, and it will always create a sigmoid function only. So corresponding to the input that we give, so that's what it's supervised learning. The corresponding to the input that we give, it will predict, it will create a model, and it will predict accordingly.
Thank you, sir. Thank you.
Hello,
Yeah.
sir.
Yeah.
Sir, the graph is gradually changing in this classification now, sir. Is it possible it is directly, if there is any change, will it change directly to 1, 0 to 1? Is it possible in this graph?
Like as you change the like the as you change the points, the value of points, the graph will change accordingly. It will the model
Like
we are training, it will
like in,
accordingly
sir,
change the
like,
values.
okay, sir. Like in the sigmoid function, is it possible like only 0 to 1?
Yeah.
Is it okay? Possible, sir?
What?
In this sigmoid function, it is going it is, if it is showing less than 0.5, it is going to 0, and if it is greater than 0.5, it is showing 1. But
Yeah.
if there without 0.5, without actual occurrence of 0.5, only zeros and ones, like with only shifting their positions.
No, what we are doing is like let's assume this point. So
Yes,
it
sir.
will predict a value of 0.9, nearly 0.9. We will have the output as 0.9, but we don't want an output as 0.9. We want the output by either 0 or 1. So we set a threshold that if the value is greater than 0.5, predict that value to be 1. And if the value is less than 0.5, predict that value to be 0.
Okay, sir.
Hello, sir.
Yeah.
Sir, if it is less than 0.5, it will predict 0, and if it is more than 0.5, it will predict 1. What
Yeah.
happens if we don't give a condition for equal to 0.5, and what will it predict, sir?
Okay, so if we don't give a threshold of 0.5, let's assume we have got the output as 0.6. So 0.6 is the probability of it being 1, and 0.4 will be the probability of it being 0.
Sir, what if it is 0.5, sir?
0.5 means it itself is like confused what it is giving equal weightage to both the classes, that he is not sure if it's 0 or 1. It is giving equal weightage that it can be 0 to it can be 1 to. But for greater than 0.5, we generally tell it to predict 1.
Yes, sir. Thank you,
In
sir.
that case, we can't do anything because uh, it's the model that we are training. So that's machine learning. No? We have left it on it to predict and give an answer. We are not having any say in that. We just give it the input and it will predict the output.
Yes, sir.
Someone is talking about multi-class function. For multi-class function, you can't use sigmoid function because sigmoid function can give values just between 0 and 1. So it is used just for the binary classification. For multi-class function, uh, now it's difficult to explain it without demonstrating, but there are you predict the you let's assume you have four classes to predict between. So finally, you will get the probability of there's another function like you use something called softmax. Now I don't want to go there. It's the last topic, but it predicts the probability of each class. Like assume you have four functions 0, 1, 2, 3, 4, 0, 1, 2, 3. So it will predict the probability of each class, and the class with the highest probability will be selected. And the sum of all the probabilities will be equal to 1, obviously.
Yes, sir. Thank you, sir.
It is not naive. Most of the classification problems are either it is true or false. For complex classifications, as I said, the functions are also complex and it can't be covered. And it's outside the scope of this lecture. But yeah, there you can have complex classifications. You can classify the things into more than uh, like more than like as many as classes you want. But the most basic one, the thing that can be covered in such less amount of time is the logistic regression, which classifies the problem into 0 and 1. So let's move on. So here also the cost function becomes something like this -1 by sigma. So I saw someone asking, how do we get this? So the y is the original data, that original output that we have. So if y is original output is like 0, uh, we get this value becomes 0, and we are just left with log 1 minus f. If the original output is 1, this value becomes 0, and we just get log f. So log f is again the way of calculating the cost. It's like the cost function that we get, and using this uh, like similar to what we got in regression, by taking the error between what has been predicted and what is the correct value. Similarly, the cost function here is predicted by what is given and what we get. And here also our objective is to minimize the cost function. So what we learned now was two different types of supervised learning, regression and classification. What is the basic difference between regression and classification? In regression, we predict numbers, while in classification, we predict categories. In regression, there can be infinite number of possible outcomes, like between 0 and 1 itself, there can be unlimited, infinite number of possible outcomes. So, and in classification, the value of outcome is very small, like only the number of classes that we give is the possible outcomes that we can have. But in regression, there can be infinite possible outcomes. Examples of regression can be any prediction, any number prediction, such as stock price prediction, house price prediction, or how demand forecasting. That means how much of the stock is required or how much would the demand of that stock. Anything related to a continuous value. Regression predicts continuous values of continuous output values. Or classification predicts discrete output values, which involves FAM detection, image recognition, sentiment analysis. Sentiment analysis means if it's good or it's bad, if a tone of like you use in word or anything, there are different tones you can write in formal, casual, professional. So it identifies by reading the data, if the reading the text, that if the text is casual, professional, formal, informal. So that is sentiment analysis. Also, in any model that we use, we can't give an input as any text or string. We need to give an input as any number only. That's when classification we convert yes or no to 0 and 1. Because the machine can't understand texts. It will understand only the numbers, the digits. So that's why we need to convert all of our data into numbers only. So for classification, we convert these classes into different discrete numbers. So we are done with supervised learning. If you guys have any doubt, you can. What signifies cost function is the error that you get. Cost function. Why do we need a sigmoid function in case of classification? Because we need a value for we need either 0 or we need either 1. And sigmoid function gives the values between 0 and 1. So if it's close to 0, we will predict 0. If it is close to 1, we will predict 1. That's why we need sigmoid function in case of binary classification. And again, cost function signifies the deviation that is from the deviation that we get from the original data. Yes, as someone said that complex problems can be divided into smaller binary problems. Like if there are 4 classes, it will first split between if it is we will first split between 2 classes. If this is this or this, if we get one thing, then we will again extend it to multiple classes. So binary classification is the basis of everything. It is used for complex classifications also, but complex classifications is we won't be able to cover in this lecture. How to choose which
Okay.
cost function? What?
So we had, sorry to cut you off, but we had
Yeah.
said that we have the function of z and all, no, sir. So what does it actually represent in case of the real life example? If we take the cancer example, you said like the size of tuberculosis. So how can we like what does the z, the function of z, those represent in when it comes to real life scenarios?
Yeah. So you saw in regression, right, that we wrote y cap as wx plus b. So here z will predict a number, any number corresponding to that x. But we don't need a number in this case. There's not any physical significance of z, but z is required for classification because we will put we'll put z equals to wx plus b later. So z is what we calculate as wx plus b. It's just a way of saying that z doesn't have any meaning here. It's just to show the function, the sigmoid function, what the sigmoid function is. We will replace z with wx plus b. So that's the thing that matters to us. This z is used to just show what is sigmoid function.
Yes, sir. Okay, sir. Thank you, sir.
Yeah. Yeah. If we want to say that if I will give an example of astronomy here in image classification. Let's say we have given it a data set of different types of galaxies, elliptical, spiral, and those different kinds of galaxies. So it will classify the image if it is a spiral galaxy, if it is a elliptical galaxy, or the different classes. So that's how classification comes under image classification. It's image classification. So that image classification comes under classification. There's other thing also, such as like using an image to get extract features out of it. We will like if possible we'll get into that later. So now the supervised learning part is done. Now we'll go to unsupervised learning. So can anyone tell what is unsupervised learning? Does anyone want to answer? Yeah, Malvika. Okay.
Is it
Yeah.
is it like they are not given prior data, or they are not monitored continuously based on a particular data?
No, the thing in unsupervised learning is someone told in like chat, we don't give it an out, like we don't tell it explicitly what should be the output of this input. We just give it the input. We just give the values that we have, and it automatically classifies it into, like, it tries to uh, identify a pattern between that data. So we are not labeling the data as we did in supervised learning. We are not telling it what is the right answer. We are telling it to give us some pattern by studying the data. The different types of unsupervised learning that we will look. So analyzing unlabeled data, it doesn't know the output yet. It just knows the input, and it will try to recognize a pattern to identify patterns and relationships. The data is not labeled with any predefined categories or outcomes. So the algorithm must find patterns and relationships on its own. So the first type of unsupervised learning, and maybe the most common, is clustering, like dividing the data into different clusters. We didn't initially tell it that this data point belongs to cluster 2, or this data point belongs to cluster 1, or this data point belongs to cluster 0. It takes all the input values and identifies that, oh, this all points are close to each other, and uh, creates a cluster out of it. It will predict, it can see that these all points are close to each other, and it will create a cluster of it. And similarly for this. So we have not told it prior that which data point belongs to which cluster. We have just given it the input, and it tries to create clusters of its own. So the definitions group similar data points together into clusters based on their features. It involves identifying patterns and structures in data without using predefined labels. Okay, so we didn't actually tell it that we didn't tell the data that the model that this data point belongs to cluster 0, but it identifies that these all points are close to each other and it creates a cluster out of it. The application is customer segmentation, like segmenting different types of customers based on their purchasing habits, that if they purchase on the weekends or if they purchase uh, during the night, or what kind of things they purchase. That is the application of one of the applications of clustering. We cluster the items into we segment the items into different clusters. I hope clustering is clear. We can't go into the algorithm of clustering right now because it will take a lot of time. The motive of this lecture is to just give a basic overview of machine learning and get into astronomy. So let's move ahead. Another type of unsupervised learning is anomaly detection. What is anomaly? Someone asked me if there is some exception or something. Like if the data deviates from the uh, pattern or a line. Let's say we have uh, this is the data between time and temperature of like anywhere. This is the x-axis denotes time and the y-axis denotes temperature. So these all data points lie near a single line. The values are nearly constant here, but there are some points where the data deviates from the pattern. It deviates from what has been going on. So that is called anomaly. So we give this input to the model, and it identifies the points that deviate from what is normal or what is considered to be normal within the data set. So it will say that, oh, these points are not anomalous, these are normal points, but these points in white, yes, these are anomalous because they deviate from the data, they deviate from the normal data. It can be used in fraud detection. Let's assume that the things are going well, the stock market prices are okay, fine, having some constant pattern or something, but uh, suddenly in a day it goes for like um, it increases 20% or something. So that's kind of anomaly, something that doesn't happen very uh, occasionally, or normally, something that happens rarely. And it identifies those rare events when the data deviates from the normal data. I hope it's clear. Yeah, someone give an example of unsupervised learning. Yeah, you gave it the questions and it separates those questions based on the subjects. So we haven't actually told it that uh, this question belongs to this subject, but it identifies that this questions, this all questions might belong to one single subject, and it will cluster that subject. Mm. Yes, Ankita, you can speak.
Hello.
Yeah,
Sir, can you tell where this part of the machine learning we use for astronomy?
this anomaly detection.
Sir, yes.
Yeah, so uh, you are like stu studying let's assume a star. You are studying its with time. What's the brightness of that star? What's the uh, emissions that it like the radiation that it emit? But on an uh, on some day you realize that the brightness has increased significantly, or the radiations have increased significantly. So you can assume that something is going on with that star. Like the real life application in astronomy is the detection of supernovae or something that we can't see with our eyes, or we can't even see it. But the brightness or the radiations or the other features change. The machine is able to recognize that something is going on with that star.
Okay, sir. Thank you.
Hello,
Yeah.
am I audible?
Yes. Yes.
Okay, so I wanted to ask that you just said there was supernova and those are those all spectroscopic data? Means all those visible light and
Yeah.
those rays?
We mostly use spectroscopy data for those kinds of things, like analyzing the stars or galaxies or the exoplanets or different things. We mostly use the spectroscopy data only.
Okay, so one more question: is this type of data is treated as a data means values or as an image?
Uh, like mostly, if you put in different images of stars, you won't be able to like differentiate it largely just based on image. So you give it different features, like as you told, the spectroscopy data, its brightness, the different spectrum it showcases, the radiation it releases, its position, different features. Those features, the numerical data is mostly used. For
Okay,
images also you can use, but the images should differentiate a bit. You can use images to classify galaxies. You can use images to like differentiate between things. But when the
yeah, for galaxies it is fine. We can get RGB images. Those are that's fine. But
yeah
I was mainly interested in the spectroscopic data, so that's the
yeah,
only reason.
so mostly we use the spectroscopic features such as those brightness, luminosity, temperature, and other things.
Okay, thank you.
Yeah, yeah. So those were the two. Yeah.
Sir, once again, will you tell about this anomaly detection, sir? I was not able
Anomaly,
to.
yeah, okay. Anomaly detection is basically identifying the points that deviate from the. As I gave the example, a star, we are studying a star, we are observing a star for a long time. Suddenly, we realize that its temperature has increased or something has happened. So that's an anomaly, something that doesn't happen very normally, something that happens very rarely. So that is anomaly. So we give the model just the data points, and it identifies if the given point is normal or it's an anomaly. I hope it's clear now.
Hello, sir.
Yeah.
Sir, can we use this model to find out peaks in the data? For example, if we are considering radiation pattern of, let's say, an isotope, we will get many
Yeah.
peaks in data, right?
Yeah.
So can we use this model to identify those peaks?
You can only if the its original radiation levels are very low as compared to the peak level. If the peak level deviates very significantly from the original levels, then you can use that without any doubt. But if the values are very similar and you say that the normal levels are 0.5, and if you want to predict the peak at 0.6, it won't be able to do that because the values are constant. But if you say
So
that the normal values are, yeah,
uh, there must be some tolerance level to this model, right? So as you said,
yeah,
if there is
yeah,
only a
that's
change
it.
of point, so how do
Yeah.
can we adjust that tolerance level?
Yeah, we can adjust the tolerance level. We can give it a threshold that if the data deviates more than this, we will have to call it an anomaly.
Okay, thank you, sir.
Yeah,
Good morning, sir.
yeah,
My question is that when we take pictures of galaxies and maybe we are using
yeah,
ML to classify them into spiral, non-barred, and stuff like that. So sometimes when we take pictures of a spiral galaxy, we might take it from a different angle. It might appear to be a plain galaxy or
yeah.
irregular galaxy. So what do we do in such cases? Can we still use ML?
Yeah. So the thing is that when you use image classification, you need to give it a standardized set of images. You can't give it images in different orientations and expect it to give the right value. Or other thing that you can do is give the like images for all the galaxies from all the orientations. You like, let's say there's a spiral galaxy, you give it. I know you can't take images for galaxies from different orientations, but just saying that if you use image classification, you need to give it images from like different perspectives. And if you can't get that data, the data should be standardized. Like it should be clearly visible in the original data set that we give that it is spiral or elliptical or something.
Understood, sir. Thank you.
Yeah. Yeah. Okay, so we'll move on. So we are done with supervised and unsupervised learning. There's another third type of type of ML called reinforcement learning, which is which whose use case is very limited but very significant in astronomy. Like reinforcement learning is the model learns from its mistakes. Let's assume uh, its uh, its most useful application is the rovers that we send on Mars or lunar rovers or something. We can't always control them from the Earth. It's not like a joystick that we say go here, go there, do this, do that. So it's reinforcement learning. We train it so much that it starts. It's just how the robots learn how to move. They start. If it goes in wrong direction, we give it a punishment. We like give it negative points. If it does the right thing, we give it positive points. Similarly, the points vary. If it crashes, we give it thousands of negative points. If it achieves something, we give it significantly large amount of positive points, so that it learns what is right and what is wrong. Like also assume that a rover has a scanner on it. It scans something. So we have trained it this much. It's reinforced it this much that it will look at this and it will realize, oh, I have to like drill it or I don't have to drill it. So that's a reinforcement learning. It has done all the mistakes in the past while we were training it, and using those mistakes and things that it did correctly, it will avoid those mistakes in future and do the things that are right. We will see cool animation later regarding reinforcement learning. Till then, now move on to the need of ML in astronomy. So, what is the need of ML in astronomy? So astronomy first is handling big data. Astronomy creates a large amount of data through telescopes, satellites, and different simulations. We we can't just look at that data ourselves and make something sense out of it because it's very large data. We need to use advanced ML algorithms to make sense out of those data. Exploration, data-driven discovery, like mostly to like identify rare events, new events that are not normal, like basically anomaly detection, something like discovery of a supernova, discovery of an exoplanet, or something like this. So that we can do using astronomy. Real-time decision making, such as I told for uh, rovers or setting up telescopes such that it identifies the conditions, it identifies the position, time, and it accordingly adjusts itself so that we can have a look at the best possible things and not waste our time looking here and there. Also, automated detection and classification, like detecting celestial objects, classifying them into stars, galaxies, asteroids, or all these things. That's why we need ML in astronomy. There's very very high use or like very advanced use cases of astronomy, ML in astronomy, but we'll try to look at some basic ones when we implement applications. So the applications of supervised learning. This exoplanet discovery. This is something that can come under both classification and anomaly detection. So we use a method called transit method. I will show you this video. So see, there's a star. Assume it to be not. It's not sun. Assume it to be any star in Milky Way galaxy, and we like track its brightness. But when the planet goes from a front of it, its brightness decreases a bit. So we can use this type of flux to like classify. Uh, we can use this in classification also that we'll be implementing later, and we can use this as anomaly detection also. So this is one use case of uh, sorry, yeah, this is one use case of supervised learning. Other one is asteroid hazardness prediction. If we need to predict if an asteroid is hazardous or not. So using different features such as its size, its position, its location, its speed, and all, we can predict if it's hazardous or not. We have a demo for this specific application in some time. Object classification, classifying an object into like the basic thing is you can see many models classifying the objects into stars, galaxies, and quasars. So it uses different spectroscopy data, temperature, luminosity, brightness, radiations, other spectral data to classify the objects into different classes. We can use this to measure the distance of the galaxies. We can also use it for solar activity forecasting. Can anyone tell me why is solar activity forecasting important? What's the real use case of solar activity forecasting? Yes, I will share the presentation after the class. Yes, Swastika?
So that we
Yeah, predicting solar storms. Why is it that important predicting solar storms? Solar storms, we can predict solar storms based on the position of the sunspots or different features such as the, yeah, it can affect communication with satellites. Not predict death of stars. It's solar, na? We are not predicting. Uh, we are not predicting like when a sun die, we are predicting, how it will affect the communications. When there's a solar storm, you might have like received some messages during when there's a solar storm that the network will not be available from this time to this time. It will affect the satellites. So we need to predict from it is used to predict that when those things can happen, when a solar storm might come, and accordingly we can set a satellite not to go there at that time. Studying sun gives idea about other stars also, but we are activating we are tracking its activity mainly for identifying sunspots and solar storms. The different uh, applications of unsupervised learning are galaxy morphology, like based on the shapes and structures, clustering them into different types of galaxies. This can be done using supervised also. This can be done using clustering also, grouping similar type of galaxies in a cluster. So that would be use case of unsupervised learning. Star clusters, identify star clusters, stellar associations. Also, unusual astronomical events, as I told that something deviates from the normal data, something that is not very normal, something that is rare, such as supernovae or gamma ray bursts or other such phenomena that doesn't happen normally. Just taking a star, it is normal, but suddenly its uh, values change, its data changes suddenly. So that's anomaly, something that deviates from its normal data. So we can use the unsupervised learning for these use cases. And reinforcement learning, autonomous maneuvering of the satellites. As I told, if we can predict that something might happen in that region in space, like an asteroid might come there, the satellite might be able to identify that and automatically change its position so that it doesn't collide with that, or while we send any satellite to any other planet. So we use this so that it can tackle any obstacles that come in the way, if any. Rover navigation, such as the Curiosity and the Perseverance rovers that were sent to Mars, they had a very high applications of reinforcement learning in them. We ca- we They did most of the tasks on their own. We weren't controlling them like go here, go there. So that's application of reinforcement learning. Also, telescope observation scheduling to prioritize targets based on their importance, the weather conditions, availability. Like they might be visible now, there's an obstacle in the way. So we can schedule like when the how the telescopes where the telescopes look, when they look. So these are the applications of reinforcement learning. You will understand reinforcement learning using this slide. Let's assume we need to send a lander on moon. So it can do following for actions. It can either do nothing, uh, like stay there where it is, or it can fire the right engine, it can fire the main engine, or it can fire the left engine, and it gets rewards accordingly. Like if it lands on the launching pad and comes to the rest, it gets about 100 points. If it moves away from landing pad, it loses reward. If it crashes, it gets minus 100 points. If it comes to a rest it gives plus 100 points. So we are telling it what things you are doing are right and what things you are doing are wrong, so that it doesn't repeat the wrong things again and again. So we are giving it rewards or punishments. Uh, the thing that we do with children and all, we just tell them that this thing is right and this thing is wrong. So this is reinforcement learning. It experiments by doing multiple things, and for each thing we tell it if it's right or if it's wrong. It's a very like time-taking process of training any robot or simulator, but the astronomers there take that time and train them accordingly, telling them that this is right, this is wrong, you should do this, you shouldn't do that. And also for using the engines and all, you need to use the minimum resources. So it can't keep firing the main engine all the time. So also when it does some action that requires some resource, it loses some point. Not a lot of point, but a little bit, some amount of points, so that it knows that what you are doing is correct, but doing a lot of it can exhaust all the resources. So that it does uh, those actions in keep those actions in check. So I hope the presentation is done now. We will have a demo of asteroid hazardness prediction. If anyone has any doubts, you can ask them now. Okay, someone's yeah, so obviously, the thing about exoplanet, that's why I put it in the supervised learning part, that we classify based upon its flux. We will see what I'm saying, but it can come under anomaly also. We look at a short period of time and we just want to check if there's a time where it significantly deviates from where the brightness significantly deviates. We aren't taking multiple periods of it. Yeah, when the brightness of stars dips, the thing that I showed in that video, that the brightness is currently straight, but when the when the planet goes from front of it, its brightness dips. So it's a behavior that is not normal according to it, right? So that's why we can also use under anomaly detection, but mostly it is used as classification, and I will tell you how we will have an implementation after. Yeah, wait. Sorry, I can't pronounce your name. You can ask the question. Yeah,
Hello, sir.
yeah,
Sir, can you once again please give the slide of moon lander simulation?
yeah. Just a minute. Yeah,
Sir, moon lander, that slide, this part.
yeah, yeah.
Sir, sir, this rewards is what why we given in this slide.
Yeah, oh, that's what I told him. We in reinforcement learning, we need to give rewards to the agent that is like the agent here is the moonlander. We tell it if we give it positive points or more points, we tell it that what you have done or what you are doing is correct. But if we give it negative points, we tell it that what you are doing is wrong. So that's why we have to keep a reward system.
Okay.
Okay. So if is there a possibility to have spectrum beyond what we know currently? I don't understand what you're asking, but yeah, that if there's something that we don't know correctly, and if a telescope or something identifies some kind of thing, then it classifies it as anomaly, and then we can have a better look at what it has classified as anomaly and find which can lead to new discoveries. So new discoveries uh, um, uh, nowadays when new discoveries in astronomy mostly comes from anomaly detection, something that hasn't been seen before, and it classifies it as abnormal. Abnormal not always means it's bad. Abnormal means that it's something that isn't uh, normal, that is something very rare. Okay, so let's now look at the demonstration for the asteroid hazardness. I will share the collab with you guys later, which you can run on your own system, like which you can run on the collab software only. And the data file I will also give you. I will just show you once how to use that collab file. Yeah, so I hope you can see my screen here. This is the Collab notebook where I have implemented the asteroid hazardness. And to run this, you don't have to actually download it on your system. You can run it on the Collab software only. Just that there's a file called asteroid data.csv. So uh, you will have, I will give the link for that file also. You'll have to just click here on the folder part and add a file with this asteroid data so that you can access, so that your model can access that file. I have already done here, and I will show you it in my system in the Visual Studio. Is my screen visible? Mizal or Badansh, can you confirm? Yeah, okay, thank you. So yeah, so the first thing that we'll implement is predicting if an asteroid is hazardous or if it's okay. So training any machine learning model requires some steps that we need to do. First is setting up the environment, such as importing libraries and loading data. If you don't know Python, then also it's not a problem. I will explain everything. So Python is one of the most versatile languages where you can like do anything you want. So there are so there are predefined functions in Python, such as print or sort or like show or something. These are the predefined libraries of Python itself. But for some advanced features, we need to import libraries. Libraries also have predefined features. So we will import four such libraries: NumPy, Pandas, Matplotlib, and Seaborn. NumPy is used for linear algebra kind of things, such as creating an array or other things to play with numbers. Pandas is used for dealing with data sets. Matplotlib is used for plotting, and Seaborn is also used for advanced plotting. So we'll first load the data. There's a syntax to do all these things. You can just have a look at what I have written and you will understand. So we are saying that data equals to pd.read CSV asteroid data. If I run this, it will read the the CSV data, which is the asteroid data, and it will like after that we use data.head. So it lists out the first 10 uh, points in the data. If you use data.sample, it will list down 10 random values from the data. And if we use data.tail, it will give us the last 10 values of the data. We'll once have a look at the data here. So this is data that we have. We have 15,635 rows and 16 columns. So 15,635 rows are the different asteroids data that we have, and 16 columns are different features that we have. And out of that one, whether this hazardous, false or true, is the output label. We want to classify our data as either true or false. So this is the output label. And other things are the input features. So we will do data analysis now. So these are the different features that we have: object name, epoch, orbit axis, orbit eccentricity. This all, you don't have to understand the meaning of everything. Even I also don't understand the meaning of each and everything. But it I've given a brief description of every every feature here, and we need to like use these features to predict what our asteroid is hazardous or not. Can anyone look at this features and tell me what do you think are the two most important features that might affect our model the most? AU, oh, which AU? There are multiple things with AU unit. Does anyone want to answer this? Yeah, minimum orbit intersection data is distance is one of the features that will be very important. Eccentricity is important, but not that important. You will get to know later. Other important feature that you guys are missing is the asteroid magnitude. You guys know how the magnitude is. What's the convention of magnitude? The lesser the magnitude, the brighter it is. And if it is brighter, it is highly possible because the asteroid doesn't have a light of its own. So the brighter it is, the more chances it has to be closer to us. So the asteroid magnitude and the minimum orbit intersection distance are the two features that might be the most important according to our initial analysis. We will get to know what are the most important features according to the model later also. Yeah, so we'll use this feature called info to get the info of all the columns that we have. It shows what is the data type of the column and how many counts of that column are there, like how many columns that value is there. So data type is either object, int 64 or float 64 or boolean. Boolean means either true or false. Object means a string value or yes, no, or other thing that is not a number. Float is decimal point, integer is the integer obviously. So first step is we will check the missing values from the data. So using that we use this null. This null means is missing and sum of all the columns. So why is it important to like identify the missing values? Because if we want to train the model, we need to like give it complete data. We can't give it incomplete data with missing values, which will lead to discrepancies in the model. So we can see that there's one column where asteroid magnitude is not given in the data. As you can see, I have given that column here. Here the asteroid magnitude we don't know, and therefore we will remove that this row from our data. And so now if we again do this use this function, we will see that now there are no missing values and we have complete data. Then we will check duplicate values if any row is duplicated once or more than one time. Why is it important to do this? Because if there are duplicate values, the data might favor that row a bit because it has got multiple input for that feature. So we can see there are no duplicate data. There is no duplicate data in our data. So we will move ahead. We use describe feature to get to know the minimum, maximum, and mean of any feature. So we can see that minimum orbit intersection distance, the minimum of this value is 0. That means that the orbit of asteroid intersects with the orbit of Earth. So it can potentially be hazardous. We'll look as we go down, you will understand better. But this describe feature is used to find the minimum, maximum, and mean of each and every column. If you remember, I told you earlier that we can't give input as any string. Here in our data, it's in hazardous column, it's written either false and true. We can't give it false and true. We need to convert it into numbers. So we will convert false equals to 0, data hazardous, 0 if value equals to false, else 1 for value in data hazardous. So if the value there is false, it will write it as 0, and if the value there is true, it will write it as 1. Now we will see some plots. So in our data, these are the number of asteroids, around 14,000 that are non-hazardous and around 2,000 that are hazardous. So we'll implement a model to identify which one is hazardous and which one isn't. So we also plot hazardous and non-hazardous based on different classifications of the asteroid. So these are the four classifications of the near-Earth asteroids, the asteroids that are found near the Earth. So the four classes are, you can see that one is Amor, who's like that doesn't cross the Earth, it rotates around the Earth. Okay, so it might potentially be less uh, hazardous as compared to others. As you can see, the amount of hazardous asteroids in Amor asteroids is less as compared to Apollo asteroids. Apollo asteroids are the asteroids that cross the Earth. 18 similarly, they cross the Earth. It's just that in 18 the semi-major axis is less than 1 astronomical units, and in Apollo their semi-major axis is greater than 1 astronomical units. And there are inner Earth objects also called apohill. Also, you can see that they are also not. There are not many asteroids that are classified as apohill because their orbit for an orbit being inside of Earth's orbit is very less seen. So there isn't much data for apohill asteroids, and they are not very hazardous too if they are. So as I told here that we can see that classification the values are uh, uh, in strings, MR or apohill or Apollo or Aten. So we convert them into numbers, convert them also in numbers that write it as 0 if it is MR, 1 if it is Apollo, 2 if it is Aten, and 3 if it is apohill. Now we see if we see the data, we can see that all the columns have numerical data apart from object name. So we have like cleaned our data and given it in a form that we can give to the model. For now, we drop the object name, we remove the object name from our data. We can later incorporate it again because the indexes are always the same. So even if we drop the object name, we can later get it back. So we are dropping the object name now. We will just use the asteroid ID, this index number, to predict if the asteroid is hazardous or not. So now, X, the input features are all the features other than hazardous, from epoch to classification, and the hazardous column is now our output label, the thing that we need to predict. So you might be wondering that we already know that all the asteroids are either hazardous or not. So what we do is we take some data and use that for training and remove out some data. Let's assume we take 70% of data for training and remove 30% of data from that. So for 30% of data, we don't know if it is hazardous or not. We know it for this just 70% of it. So using that 70% of data, we will create a model, and that model will predict if the other 30% of asteroids are hazardous or not. So if a new asteroid comes into uh, if a new asteroid later comes into existence, we can check if it's hazardous or not. You need to run all these columns. Just make sure that you run all this. Yeah, so now the X is the input features, all those numerical values other than if it is hazardous or not, and Y is the output label, if it is hazardous or not. Again, we'll describe it's fine. Now, as I told, we need to split the data. And before that, we need to scale the data. Sorry. You need to first import this and then use this. Can anyone tell me why we need to scale the data and what is scaling? Okay, someone is asking why are we not using 100% data for training? If we use 100% data for training, then what will we test our data upon. We need something to test our model, na? So that's why we just take the 70%. Yeah, rest is used for testing and validation. Yeah, so some does someone want to answer why we need to scale our data?
Sir, what is the scale of hazardness? Like, how can we measure it?
I don't get it what you're asking. Like, what is scale of hazardness means?
Like, how hazard a asteroid is?
We are not predicting it's how hazardous it is. We are predicting if it is hazardous or if it is not hazardous. And to answer your question, as I told, just we calculate the probability. We can get if we get the data 0.7. Let's assume you get the output as 0.7. That means 70% chance of it being hazardous, and we put threshold on 50%. So if the value is greater than 50%, we mark it as hazardous. If the value is less than 50%, we mark it as non-hazardous.
Okay.
Yeah. Okay. So I assume you don't know scaling. So scaling is used because, as you can see, for all the data, the mean, the average is very variable, and the data is the ranges vary a lot. Like the classification just varies from 0 to 3. The magnitude just varies from a minimum to maximum of 9.4 to 22.2. The this orbital reference varies from 1 to 21, while the epoch varies from uh, like 44221 to 57800. So it's very unbalanced data. Like the features are very variable, varying from each other. So that's why we use a scaler. For this, we will use this standard scaler, which scales all the data such that it the average value for that column is now 0, and standard deviation for that column is 1. It doesn't matter if you scale or like you might be assuming that if we change the data, like scale it, it might lead to wrong results, but it is not true because you're scaling all the columns in the similar way. So as you are scaling all the columns in the similar way, now it just need to change its parameters W and B to get the correct results. So it isn't true that scaling will lead to wrong results. I will show you this scaled data, X scaled. So see this orbit axis. If you click on this, you can see that mean is minus 3.2 to 10 to the power minus 17. That is very close to 0. The standard deviation is close to 1. So now what it has done is it has create the average of all the columns is now close to 0, and standard deviation of all the columns is now close to 1. You can see it for every column. So this allows our data to be standardized, scaled so that the model can comprehend it better. Now we will split the data. So we will split it into X-train, X-test, Y-train, Y-test. X-train are the features for training. X-test are the features for testing, and Y-train are the features for output labels for training, and Y-test are the output labels for testing. So we split this scaled data, and test size equals to 0.3. That means that 30% of our data will now become testing data, and 70% of our data will now become training data. Now creating a model. There are multiple different types of classifiers: logistic regression, decision tree classifier, random forest classifier, and many more. We will use these 3 for creating a model today. Also, you can create logistic regression model by using the sigmoid function and all. But using the library, we can do it directly. In the backend, it does exactly the same thing about the sigmoid function that I told. But to make our data better, make our code better and easier to comprehend, we use the libraries. So our first model is logistic regression. So it will fit our external environment. You use model.fit to fit the training values, and then you predict the new y's using the testing data. And what is accuracy? Accuracy are the points where the y predicted is equal to y test. Yeah, what that the predicted value should be equal to the actual values. So those percentage of values is called accuracy. So if we run it now, in this short amount of time, it used the logistic regression model. It fit our data external and y train, and it predicted the values for x test, y predicted values for x test. So I will also show you y predicted one. So for different asteroids, it predicted either 0 or 1. And if you see y test also, we have for different indexes 0 or 1. So this is how logistic regression predicted whether an asteroid is hazardous or not. And now we'll use the other, which is decision tree classifier. So decision tree, it's a very interesting concept. I will show you just now what it does. So it predicted, and you can see that our accuracy with decision tree is 1. There aren't any cases where it predicted wrong value. We'll find the feature importance of according to decision tree classifier, what were the most important features. And if we plot them as expected, the asteroid magnitude is the most important feature according to the decision tree classifier. It has mostly classified its data based upon asteroid magnitude. And the second most important feature is minimum orbit intersection distance as expected. So these two features are the most important features, and it was able to classify the decision tree classifier was able to classify the asteroids as hazardous or non-hazardous using just these two columns. I will show you a cool visualization of what it does. So see this. It first looked at the minimum orbit intersection distance. It chose this value and it found the value for which after that greater than that value, all the asteroids are non-hazardous. So it uh, separated them there only. So it's like asking it a question like we ask that if for any distance, if it's non-hazardous, separate that at once. So it has separated those all asteroids whose minimum orbit intersection distance it's greater than its threshold. Then it will look at the asteroid magnitude, and it can find that for an asteroid magnitude of greater than this, all the asteroids are non-hazardous. So it will now again look at the values lower than that. And don't get confused for magnitude, as I told, as small the magnitude, the brighter it is, and more closer it is. So larger the magnitude, the less bright it is, and further away from us that is. Now again, the data that is left, it again uses the minimum orbit intersection distance and finds out that for any asteroid whose minimum orbit intersection distance is less than this value, that is hazardous. So it puts them in hazardous. And later, just two points are left, and using orbital reference, it classifies that okay, this one is hazardous and this one is non-hazardous. So this is a visualization of how the decision tree works. Also, this random forest classifier, the third model, it is a combination of multiple decision trees. There's no way to visualize this, but it combines multiple decision trees to create a forest. And here you can see that it uses other features also. It did not only use the asteroid magnitude and orbital distance, intersection distance. It used all the features with some like it gave importance to other features too. So these are the three things or three types of classifiers that we have used, and we have got an accuracy of 1 using 100% using random forest classifier and decision tree classifier. Also, logistic regression also we have not got bad results. 95.5% accuracy also great in. So, do you have any doubts now? I will share this code also with you, so don't worry. You can have a look at it later, run on your own system or run in the Colab notebook any way you want. Any doubts? Yes, data is divided into three group training. Yeah, correct. We didn't need validation here because the data validation set here because the data is not that big, but yeah, we use some part of it for testing our model. Guys, any doubts? Okay, that depends upon the classifier, right? The classifier chooses uh, uh, the decision tree classifier chose to start from the minimum orbit intersection, the asteroid magnitude, because it thought that it can uh, separate out most of the asteroids using that feature. But the other feature is dominant in other one because that model thought that it can present. I will share the collab notebook that it's a Google software that you can run online on that Google software only. Um, you don't need to like install the Visual Studio to like run this code. Why in most cases the 70% 30% rule is used. It's not in most cases you can use 80% data for training, 20% data for testing, anything. But always you need to make sure that you are giving more data for training than testing because training is the difficult part. It needs more data for training. You can't expect it to give 10% of data for training and like predict output values for 90% of data. We have run out of time, but I will just quickly go through the other demonstration. I will also how does the model know which class to prioritize? The models have been structured that way. They will know that okay, uh, in the decision tree classifier, see that it is it is able to separate out 6,018 asteroids just based upon the minimum orbit intersection distance. That's why it prioritizes this. If it was able to like separate out 4,000 like asteroids, then it would have used the asteroid magnitude to prioritize. So it depends upon the model to model. Random forest, it thought that it would be better to use the asteroid magnitude first. Okay, so I will go just very quickly go through the exoplanet prediction model. So here also the process is same, and see again here that the same video that the planet when the planet goes from front of the sun or the star, its brightness decreases. So I will again import the um, libraries. I will load the data. Here we have two different data for testing and training. So we don't have to like split our data into train and test data later. Also, the values here are given in such form that we have if we see that we have for training data, we have 5087 different stars, and the label is whether it is exoplanet or not. If it is exoplanet, it is given the value of 2. If it is not, it is given a value of 1. And flux are the different values of brightness at different points of time. So we have around 3200 columns of flux. So I will run all these things. So fine, we will check the missing values. If it's missing value, there are no missing values, we will remove that. We don't have any duplicate data also. Okay, so now we need because of convention, we will and use for using logistic regression where the output value should either be 0 or 1. We will convert the data such as when the value is 2, we will convert it to 1. That 1 is the 1 shows the presence of exoplanet, 0 shows the absence of exoplanet. Now we see that the in the training data, the number of exoplanets is close to 5,000. Close to stars which doesn't have exoplanet is close to 5,000, and the number of stars that have exoplanet is very less than 50. So it's very unbalanced. We'll come into that later, but we will now see some plots. So we will like plot for different values of stars. So this is star 2. You can see that there's dip in brightness at periodic value at regular intervals. The thing I was talking about. At regular intervals, there's a dip in its brightness. Let's check for index 16. This is also an exoplanet, but it isn't very clear in this one. So it will study the different, like here you can see that at regular intervals, there's a sudden dip in the brightness, in the flux. So you can put different index values and check yourself. Here also, now we will, the training data is all the features, all the flux values, and the label is the label column, whether it is an exoplanet or not. And we don't need to split now because we have two different exotest and exotrain for different testing and training. As I showed you here, that the data is very unbalanced. The number of exoplanets as compared to non-exoplanets is very low. So we will use something called SMOT, which is overfitting. It uses the mean and standard deviation to create some new new data points so that we have equal number of points for equal number of points for exoplanets and non-exoplanets. So if we check our data now, earlier which was 5,000 points, 5,000 rows, now is 10,000 rows. This not this, sorry, this text. So now we have 10,000, 1000 rows. So it's created new rows so that we have balanced data. Now again, we will scale this data and we will use 3 models again. It takes time to run, around a minute. I will not run it now, but the previous time I ran it, the accuracy for logistic regression was 96.1%, for decision tree it was 97.01%, and random forest it was 99.1%. I will share this with you. It's no use of using decision tree here because it's like just uh, it seems unnecessary, but I have just showed it so you can have a look of what it's doing. Can you give some tips to choose the best model for a problem? What are the correct coding etiquettes to follow? So the procedure I told you first is setting up the environment, importing all the libraries, loading the data. Will there be a chance where the precision I don't understand what is precession of a star. Oh, okay. There can be chance. Yeah, there can surely be chance. So it's saying that it can be an exoplanet or it can't be an exoplanet. It can be an exoplanet or it might not be an exoplanet. So it's not saying that it's 100% an exoplanet. It's saying after that there are other techniques also that will be used to verify if it's an exoplanet or not. But transit method is the uh, most common method used for like just to get the first intuition of a planet. How many features did you use for training? I told you we used around how many 3,000 columns of fluxes for training. So those all 3,000 columns are features. And in the asteroid one, there were around 16 features. Also, choosing the best model depends upon the type of problem you are solving. I feel that for the asteroid one, the better model was decision tree and random forest. But for this one, logistic regression is better because it's showing the probability. Decision tree classifies into the data based upon a threshold, like if it is lesser than this, and this is this. There's a KNN algorithm too. Yeah, it is used for clustering, but we don't have times to like create a model for that. But you can learn. Yeah, we can't learn it now. The time is over, and this was the things that we could do in such the given time. But the KNN model is used for clustering. Yes, Ankita.
Hello.
Yeah.
Okay, just apart from these are the general topics. I was interested in some more specialized topics. So can I ask
What?
the
What kind of specialized topics?
means I was especially interested in spectroscopic data. So what are the Python libraries that are available for these kind of data?
Python libraries are used for making handling your data. You can get spectroscopy data for the stars from a website called Kaggle. There are multiple data sets for all the topics. You can
Yeah.
get the data from there and use the similar procedure to like train your model and get the outputs. The procedure
No,
would be almost the same.
no procedure means there are Python libraries like specutils. Like what means where can I find those more detailed tutorials and all on those type of?
And what I your voice is low. Can you repeat? Sorry.
I was asking about specutils library that's available in Python, and what are the other kind of libraries to handle this kind of data?
I am very sorry. I don't know about the library you are talking about, but okay, there might be some library that can make a spectroscopy data handling better easier. You can find about it and use that to like that. I guess that library is used to like convert your spectroscopy data into better forms. I am not very sure about it, but
Okay.
yeah.
But can you recommend some tutorials or other courseworks which I can attend where I can get these kind of tutorials
Actually,
on this?
you it's very difficult to find machine learning applications for astronomy on the online. There are many less people work in this field right now, and
Yeah,
many
yeah.
even less people give tutorials for this right now. But you might get tutorials like this on YouTube, or the better option that you have is find the topic you want to uh, get a code for on Kaggle. You can just search the topic and it will give different notebooks, different codes, and different datasets for the problem you are looking for.
Okay. Okay, thank you so much.
Yeah. Do you guys have any other doubts? I will be sharing this notebook and the datasets with you so that you can run this on your system or the Collab notebook yourself. And I will once show you again how to use the Collab notebook. Yeah, so this is the Collab notebook here. It's the same way you will have to run every column individually, or you can run all the columns together using files. There might be something. Runtime here, you can run all using Control plus F9, or you can run one block at a time. And you need to upload your file here, or it won't run. You need to upload using this button. You need to upload your file, the file that is needed, asteroid data for asteroid prediction, and exotest and exotrain for exoplanet detection, and run it all. It's the same that I showed in Visual Code. It's just you can run this without installing Python and other things on your machine. You can. This is a cloud-based hardware, where you can directly run your files. Yeah, data from official sources like satellites regarding asteroids or stars is available in public domain. You just need to know the right place to search it. Like there are for getting the data for exoplanets, there you can get the Kepler data for thousands of exoplanets available on the NASA website. The asteroid data that I used was also from compiled by NASA only. So yeah, this data is available to public. You can use this. Yes, you can use API keys for real-time data also. Attendance will be automatically recorded. Can you all just please scan this feedback form to like I am not sure if this feedback form has any significance in capturing your attendance, but I would suggest once you like fill this form. Yeah, everybody fill this feedback form for your attendance, please. Yeah, I will share the links to download the mentioned data. Yes, there are numerous NASA API keys to take data from.
Can you please send the PPT?
Yeah, I will send the PPT also. I will send the PPT. I will send the codes for both of those demonstrations, and I will also send the data files. QR code won't be shared in the group. I guess it's only for the people who uh, joined the meeting. You can scan the QR code from here, or we are given the link in the chat also, so you can use that. If you guys have any other doubts, you can ask them now. Can you tell a bit about Astropia? I heard it's an important library used for astronomy data analysis. I'm sorry, I don't exactly know about it. I am I I am also not a very advanced user of machine learning, so uh, yeah, I taught you guys what I know, but you can always find these things in the you for any library you want to know, just go to the official website of that library. You will have detailed um, you will get detailed features and detailed documentation of how to use those libraries. All the libraries have their official websites of their own. I hope you guys enjoyed the session and it was insightful. Thank you for joining. Recording will be shared with you soon. The slides will also be shared, and the code and datasets also will be shared. Yes, you guys can leave now.
The assignment will be
Uh,
related ML or some theoretical topics.
There mostly won't be any assignment for this session. You will get assignments for later session and the first session. If by chance we decide to give you assignment for this session, we will let you know.
Okay, okay, thank you.
Thank you for joining.